Slides that there's no space, nothing in theory. There's not too much really to go over. So you got your wall. So this is what we've done so far. That's an interior wall. And here's the elevation view. Okay. There's our spacing. So that's one layer. Everybody, we design these studs similar to how we design columns. We assume it's a concentric load. We derive our axial load from a uniform dead load. All right, a uniform factored load, uniformly distributed load. We also might have some loads from above, which we represent. That could be an opening, for example, coming from above. All right, we talked about openings in example 7. So now where we're going is we're going to see what the difference is. What we're going to talk about exterior walls. And so if you look at the exterior walls, what we're really adding is a layer of sheathing. And then we got this concept. We got this cloud here. That's what's changing. We got wind. All right, so now we're going to look at what happens when you got wind. We've got, I'm going to call it W prime F to distinguish it from our gravity loads. For terms, We'll refer to these guys as gravity loads. And this will be lateral, be sideways, or we'll just call it wind load. Instead of wind load, we could also have soil pressure in the case of foundation walls. We're not really going to do any of that in this class, but you would have some soil or even retaining walls too, and you would have some soil pushing up against this. But for now, we're just going to talk about wind load to get the idea. So the first question, how are they the same as interior load-bearing walls? Same, they're constructed the same structure. Yeah, generally we don't have as stiff of a sheathing on the interior walls. Hopefully at the end we'll get to talk a little bit about shear walls, and then that's when you'll see some OSB on the inside. But OSB sheathing really makes it complicated to add things like light fixtures, light switches, and wall penetrations. Gypsum wallboard is a lot more flexible. So we try not to add gypsum on the inside. It's more the exception, not the rule, but definitely on the outside it's mandatory. Because the gypsum isn't water resistant, the gypsum isn't gypsum isn't water resistant, gypsum's more OSB is more durable, and so on. But yeah, just like Alex says, it's constructed the exact same way. All right, and then if you had your, just superimpose an opening quickly. All right, there would be there's a quick opening, just so we can see. Give or take, right? One jack, one king, here's the header. And it would be the same thing for exterior walls. How else are they the same as interior load-bearing walls?
The load is transferred the same, essentially.
So we got same construction without exterior sheathing. What did you say?
The load path is basically the same as it would be for an interior wall.
I'll just say for axial,
Yeah.
axial loads. Yeah. What else? Okay, with the construction, you'll have the same spacing. So we have 12-inch, 16-inch S.
But aren't your exterior walls generally spaced differently? Like in my practical experience.
Not really.
The spacings are the same.
The spacings are the same.
But like,
So these are still the same as interior walls. 12, 16, and 24. Which one am I going to say is?
we're probably gonna go 16.
We go 16 or less. 16 inches or less is typical in industry. All right, so that's the same. Same construction. Some more space here. Built laying flat, then erected on site. That doesn't change. What else do you notice is the same? Construction fault covers a lot, right? So we got studs that are spaced at a certain amount of spacing. We got 2 top plates, 2 bottom plates. That hasn't changed.
Single one.
Thank you.
That's bad dimension, man.
So For the most part, everything's the same except for this extra blue line that I've written.
And you'll probably use like a higher grade, like a.
Not necessarily, no.
Or a higher dimension, pardon me. You use
Yeah.
2x6 for an outside versus.
Oh, higher dimension, yes. So we can put, but that would be kind of how it's different. Let's talk about different. So typically 2x6. How do I shut off my? Typically 2x6. Interiors can be 2x6, 2x4, 2x6, 2x8. Typically 2x6 can be 2x8. Sometimes architects will specify 2x8 to get more insulation.
How long?
Huh?
How long?
Very little. They're instead of thickening the walls, who did building science? Have you guys done building science?
Yeah.
What happens when you put more insulation between the studs?
You dimension returns.
Why? Costs more money for the insulation, but are you usually you're trying to put more insulation to get a higher R value?
The wood still provides thermal path.
Exactly. The studs are a thermal bridge, right? Thermal bridging. So no matter how deep you make that cavity, you're going to have those studs, and then the architect will ask you to space it out to 24 or 36 inches, and you'll come back and say, no, we can't do that, right? So that's why now architects are going to this whole rigid insulation on the outside, where it's completely uniform, but that's an aside. Yes?
What about the new builders? They are building exterior walls with double 2x4 studs to get more space, to get more insulation.
Double 2x4?
Yeah.
Yeah, so I've seen 2x6 with a 2x4 kind of interior. That works, but then the problem is, again, from a moisture standpoint, right? If you gotta have your warm side on the warm side, but then all that cold air is penetrating through your outer.
2x4 spaces, they give like a space in between,
Yeah.
so that you can put more insulation and make a more high performance house.
But you'll have the same, if you put the insulation on the inside wall, then all the cold air comes in and it rests inside that outside wall where it's cold. And then if there's ever sort of any heat, it's not ideal, right? You generally want to separate your moisture vapor from the outside.
Yeah, you put a vapor barrier, but and sheeting, but instead of using a 2x6 or 2x8, they put in 2x4 space so they can have more area.
And talk about break.
Yeah, the thermal bridge, and also how does the structure goes?
Yeah.
That's my question.
I've never seen that. I've seen a 2x6 with an interior 2x4 wall. The trouble with 2x6 is when you get into the multifamily, like multi-stories, the 2x4s can't hold a lot of weight, which we'll see. So then the engineers will be like, 2x4 aren't desirable for gravity loads, and we want 2x6. And then the architects will say thermal bridging, not enough R value, and so we try to find a solution. I've seen 2x6 with a 2x4 wall inside, but typically I just see 2x6 exteriors. That's a good point. How else are they different? We've got lateral loads to consider. All right, that comes with load combinations. How else are they different?
More rigid sheeting.
Huh?
More rigid sheeting.
Oh yeah. Anything else?
They deal with lateral forces.
Sorry?
They deal with lateral forces?
Yeah, I got that. Lateral loads to consider.
No.
Load combinations. All right, and so one of the tricky things, I put load combinations in brackets here, but one of the tricky things is looking at a load combination. So what people tend to do, which is what I did when I was reviewing, it's been like 5 years since I did this. What people tend to do is they take the worst case wind and they take the worst case gravity, they put it all together and they try to design for it. But our National Building Code treats these load combinations differently. How would we approach this problem with the National Building Code? If you guys don't have your National Building Code, get it opened up. Oh, I happen to have it right here. Okay, so look at this. This is where we start to come into play. So if you look at load combination 2, we've got dead, live as the principal load, and then we got snow or wind. All right, so load combination 2. Load combination 2 takes 1.5 this, 1.25 dead, 1.5 live for the gravity, and 0.4 wind. Right, and if we had some snow, we'd have some snow. Not snow on the roof, but you guys have done lots of practice with that. So we've got to treat these separately. And then load case 3, we've got the snow if we're on the roof. Remember the clause that says we'll take the worst, whatever produces the largest effect, the live of the snow on the roof. So then if we're looking at roof load, we'll have 1.25 dead, 1.5 snow, and then again 0.4 wind. If you can see by inspection, live is greater than snow, right? You can automatically count out load case 2. Now load case 4, that's where we take the maximum effect of the wind in this load envelope, and then we take half of the live. So you'll never see 1.25 dead, 1.4 wind, it's 1.5 live, and 1.5 snow. All right, but that's what students will do. And that's where you got to be careful. And so we'll see that in the example today. I think that's good. Okay. What loads do they support? What loads do they support?
All the loads that you will report plus marginal
Let's take them into 2 gravity loads. Oh, one other thing that you might see me do is I'll do gravity loads are downwards because gravity is always down.
Positive is down.
Positive is down, gravity is always down, and then this guy I might have gotta find a sweet spot. I might put an arrow to say lateral loads and gravity loads. But we're talking about the same thing. There's gravity loads, so we got to look at what are our gravity loads? I'm gonna do this. What about wind load? When would wind load become a gravity load? Considered a gravity load? Sorry? Escarpment. You guys are doing wind and steel, right?
Yep.
So what happens on the roof with a wind load? Causes uplift, and there's also downward pressure. There's a balance between, upwards and downwards pressure depending on which face you're on. That will cause loads in the downward direction. All right, so even though it's not gravity causing those loads, they're still going to add to here. All right, so these loads from above, for example, that could include some uplift and some downward forces from the roof due to wind. So you got to be careful. Wind can be in the gravity side. when we say gravity, we're talking about, and I'll just put it right here, acting up, down, upwards and downwards. Okay, another big example of multifamily is you will have, okay, anyway, gravity loads, and we have lateral loads. This can be wind load, which is what, and then we have soil pressure, not in this course. So we got soil pressure, wind load, that's pretty much. Okay, any questions on that? Okay, what if there's an opening? We kind of talked about this. So if there's an opening, that means we're going to have sheathing that looks like this. Now this is all sheathed. All right, and then you're going to have this W prime F into page. All right, so now we got the cloud blowing on the exterior wall, which is hitting the sheathing. All right, and that's distributing the wind pressure to the studs. All right, so the load path would be, you have the pressure here, and that's getting distributed to the studs. All right, which goes into the studs and goes into the top plate. And once you're into the top plate, you're into the floor system. All right, this is load path wind. Now when you're at an opening, then you've got this load path here, but it has nowhere to go here because this is an opening, so it goes into the header. And then when it goes into the header, then it goes into the king, and it goes into the floor system via the king stud. All right, so here, what that means, that's a tribute for a stud. So that's a tribute king stud. All right, think about this as a floor where we have a beam, and this is taking gravity loads. It's very similar to the way we treat it. We treat half of the load it needs to support on the left, which is half a stud spacing, and half of the load it needs to support on the right. It needs to support everything to the next king stud. So we take the spacing between the king studs divided by 2, which if it's not clear now, I can put that in here. So this is L opening. And this is LO over 2. Okay, there's going to be a little bit more. We know the clear span, right, includes half of the bearing on each side. I just put the opening one. But basically, right, the king stud needs to hold the distance between what's on the left and what's on the right. If you have double openings, right, this will have to hold the next king stud there. So we distribute the load similar to the gravity loads, and then when it comes to the studs, they're distributed between the stud spacing. So studs are similar to joists if you want to think about it that way, and then the king studs are similar to beams. And the load gets transferred to the king studs via this header and the sheathing that's over the opening. We're not going to have to do this in the course. I might ask you some test questions, like draw the load path. All right, and basically I just want you to redraw this. I'll say draw the load path for the studs, right? And then I want you to start it in the middle of the studs, work it out, work into the studs, and work yourself into the top plate. And then if I say draw the load path for the king studs, same thing. Start it at the top of the wall, get it into the header. Header gets transferred to the king stud transfers it to the floors. Once it's in the floors, you can consider it in the building, because we haven't talked about lateral resisting systems in the building. Any questions on that? See sketch above. What ways do they fail? Okay, so if we already have we've got our stud here. And we've got our sheathing layer. When you guys draw your exterior studs, always draw exterior sheathing. All right, always draw that line because it's going to be on all the structural drawings. So when you have your wind load, what ways can this thing fail? We already.
Might bend.
Sorry?
Might bend.
Yeah, so it might bend.
Bending here, compression. Pretty much everything.
If they're sheathing from outside, that means it's laterally braced, so it's gonna buckle inside.
It's only laterally braced in the weak axis. It's not laterally braced in the strong axis. So that means we can have some extreme bending. So MR greater than MF. What else with the bending? What else will fail here?
Sheathing.
Sorry?
Sheathing.
What would fail in the sheathing?
Drywall. Cracking.
Cracking. So what causes the cracking?
Flexure.
What? Deflection. Good. Delta max greater than delta allowable. We got deflection. We got MR. What else do we got?
Swing.
Sorry?
Swing.
Swaying. Oh, good one. That's a little outside the scope of the course, but let's do it. So what do you mean by swaying?
Like, let's say there's an earthquake, the wall can move sideways.
Yeah. So that one is talking about this. Even with the wind, that's where earthquake loads. Why did we forget about earthquake? Because we don't have earthquakes here, right? I'm gonna add earthquake here. It's not in this course. All right, if you got your door. And some windows. windows. Here's the wind pressure. All right, you're saying that this thing's gonna have a tendency to okay, is that what you're talking about? So yeah, you guys deal with this in concrete or steel? All right, so if I think we're gonna have some time at the end. We'll talk about lateral resisting systems. This is a whole system failure, and we're looking at just elements. All right, so we're looking at localized, the stud or the king stud that we're looking at. We're not looking at the full building right now. So even though you have this whole swaying building, you're gonna have a bunch of kind of micro failures like this. You guys see that? So we're just focused on the elements, but good thinking. Let's think it outside the box. How else can this fail? So what do we check in bending?
Do we need to check these studs for shear?
Yes.
Natural load?
Well, yeah, so it can definitely fail in shear. I got this backwards here. Come on, guys. It was a trick. So how can it fail? Shear is less than the factored shear. The moment resistance is less than the factored moment. The deflection, the maximum deflection is greater than the allowable deflection. All right, what's the allowable deflection? L equals L over 240 for total load. L over 360, just to keep it consistent for this course. That's what we're looking at. And I'll give it to you on the test. How else can it fail?
Bearing there.
Bearing. What about bearing? It's down here, right? QR is less than QF. How else can it fail? So we focus, everything we're not focusing, we got bending members like a joist. That's good. We've got some compression parallel to the grain type failures with QR. What else with compression failures? We talked about it already. Some of the most strong access. Huh? Strong axis buckling, right? Or, so basically we're talking about PR is less than PF. Strong axis buckling. Remember, PR includes the buckling tendency and also the compressive resistance parallel to grain. All right? To remind you, plus compressive resistance parallel to grain. So see how it's the culmination of everything we've done this course? All right, we've got module 2, which is, well, module 1 is the wood products and, you know, how the constructability and all that. Module 2 is bending, which we covered with the deflection, the bearing, the shear, and the moment. And we got vibration here too. That's not such a concern because these tend to be not so long, but vibration would be a concern for tall walls. Then we also have our module 3, which is strong axis, which is a compression member theory. So we got strong axis buckling, and then we also got compression parallel to grain. Have we got them all? Torsion, not so much. Not so much. There wouldn't be torsion because of the system, everything gets loaded pretty equally and symmetrically. So torsion wouldn't be one. But there's another thing. Look, focus here. What's going to happen here? Let's draw the connections. These have been built on the ground before, so they'd have some nails. All right, say the nails are too short. If the nails are too short, what's going to happen at the bottom? What kind of connection failure? What's gonna happen? How's that stud gonna move? Shear, right? So the wind is pushing it this way, all right? It's got a reaction, a pinned reaction down here, so it has to push back. If it doesn't have capacity, you're gonna have this. You're gonna have a tendency for it to kick out. All right, and what's gonna happen is it's gonna push and push and push on those nails, and this might kind of break off, and it's gonna kick out. So we gotta make sure the nail connection is good enough for the shear from W prime F. So this would be V prime F. R is less than V prime F. Prime being the lateral direction. And so when that happens, okay, we talked about crushing, we talked about all that good stuff. So when the nails are insufficient, getting to the conclusion of all this, say the nails are really long, right? If the nail nails get too long, okay, they're going to tend to bend. Like that. Then you'll have this shifted. Okay, you're going to have a nail that's bending now. So you either have this shear failure where it comes off and it breaks the wood, or you've got bending of the nails. Has everybody kind of experienced bending of nails before? Right, eventually you push on these basically really slender columns, you'll push on those, and eventually they'll bend over. Like if you take a paper clip, push on the paper clip, that's gonna bend over. So then what we do is we start adding reinforcement. And that's why I've got this photo. All right, when the nails are insufficient for the wind, we put these steel angles, I call them clips because it's gauged, it's very thin steel. But you can see they're connected with the nails into the bottom plate or the top plate, into the plate and the stud. And this reinforces direction for F2, and we can find F2 from the W prime F that we've resolved from the wind. And then this force as well, I'm in trouble thinking about it right now. I'm in trouble, but this is, can you see how this would reinforce the nail connection?
Surface area.
So it's important to know, so if we go here.
Connection like this would work in a corner.
Here's your nail. Your nail's inside there. Something like that. I don't think that's actually helping. So I'm gonna take that off. What did you ask, Andre?
When you have, would it be possible to make a connection like this on a stud that is in a corner of the wall?
Yeah.
Because you would have like, not on both sides, one side and the other one.
Yeah, so usually these have capacities for one side, but we like to use it, we like to keep the resistance symmetrical on both sides. All right, so you'll see them installed on twos. Now when you look at the catalog specifiers, it says if it can be installed on a single 2x lumber, or if it has a minimum thickness in between, right? Because if you start adding a lot more nails to get a lot more capacity, you start having like a Swiss cheese effect on the wood, and then it says it has to be minimum 2 studs. Then you go and add 2 studs. Don't worry too much about that stuff because we're starting to get into connections. I wanted to get in connections, but that might not happen. We'll see how this goes. And so when you get into a tall wall situation, part 9 considers a tall wall. Anybody remember what it is? 3.6 meters. So anything above 3.6 meters, I think it's like 11'8". That's considered a tall wall. Engineer has to design it. So this length is just getting longer, which is going to have a larger moment, which is going to have larger shear, and that's why engineers have to step in and make sure that all of these considerations are being accounted for. So let's look at what that looks like in an example. Any questions on any of this? So I'll just put a note here, connection failure. Use clips or larger nails. And this is also connection failure.
Yeah.
Yes?
As far as I know, that's what the platform of the wall is built on the ground or whatever, on flat, and it's erect. But if you have, for example, 4 or 5 story building, you're gonna have to erect it somewhere with a crane, whatever. Do you need to check the studs for tension while you are erecting them?
You wouldn't erect 4 or 5 stories at once. At one
No, I
time.
mean, even if it's just for 1 story, but.
Like the temporary loads while it's erecting?
Yeah,
No. No. These will be built solid enough that they can withstand those temporary forces.
Because pre-test, we need to check things like this.
Yeah, and that's, I think
Yeah.
that's because of the dead load of
Maybe.
concrete.
Yeah, makes sense.
And also, but also they tend to be very long and slender. These guys here, you're usually not erecting more than 9 or 10 feet at a time. And so, and then when you go to build the tall walls, that's where you might run into an issue. But you have the whole 3 sides of the building built, and you're basically leaning up big posts, big studs, connecting them in, and you kind of build those ones in place. So the difference with the tall walls, let's see if I can show you a tall wall photo. We'll see if we can get it. I like to do a tall wall example, but honestly, so this is a regular tall wall with long studs. This is a regular tall wall with long studs, and depending on you might use a crane to lift something like this, right? But do you guys remember that tall wall that was in? When did I show you that one? I'll have to show you later on. But then you're starting to come into the case-by-case basis. So right now we're gonna just focus on platform style construction, all right, where you're still building this stuff on the ground, erecting it into place, and then placing your floors on top. One of the things too is as you get higher and higher on the stories, you now need to prevent, when you're temporarily erecting this wall, you need to prevent it from falling over. Have you dealt with this? Have you dealt with this? Right, so once you're on the 2nd floor and you have these outside walls, they'll have a tendency to fall over and fall onto the ground. And that's happened to me before. All right, and so you do have to provide some temporary restraint on this side. all right? Or you have to pull back enough on this side to make sure that that doesn't fall over. Not usually, like people don't usually push the wall over, but what happens is you stand them and your bracing's insufficient and a big wind gust starts, and then all those walls pull down. And once one goes, right, even though the other ones have openings and lets the wind through, it just pulls it down like a big train. So, has anybody experienced that before?
Not actually falling down, but I don't know.
Maybe.
Yeah, like I've been on sites that I worked on where it happened, and then also as a designer, I got calls from site saying, you know, big windstorm, Airdrie gets really windy. We were building in Airdrie, and it just took it down. So temporary bracing is a consideration you guys don't have to worry about, but think about it. Contractors and framers have to think about it more. Okay, let's go to the example. This is a good time to take a break. Come back in 10 minutes, 5 after 9.
Do you remember? I think when we left it, I don't know.
I asked Moy if it's safe, he said yeah, so hopefully it's like
It doesn't matter. If you guys left, yeah, it's fine. Oh, you guys are staying after school, correct?
To do what? This?
So, because I forgot to show it. I was like 4 days late.
Tomorrow.
I mean, mine for this
Dentist appointment tomorrow.
They're gonna stay tonight.
I mean, still has to be solved and concrete. Not even talk about steel. What is steel mean? Concrete is due Friday, Saturday.
When you have a wall not supporting the wall,
Yeah. I think what I want you what other loads are there? Yeah. Self-weight of the wall. Then normally there would be the ceiling as well. Sometimes there would be ceiling too if there's a drop ceiling, which is not clear here. And it says assume it doesn't support, so all I wanted to see was calculate self-weights. Say do it 24 inches, or 24 inches.
The whole of last night, I was thinking about this. I woke up in the morning, I'm thinking about this. I didn't. I was there. Because I entered maybe at 11. Yeah. Took a shower, washed all my, what's this? My mug and water bottle plus the lunch thing.
Are you staying after school again today?
We have still in the moment. One of them has to be.
We have to use our.
When you design it,
Nah.
Concrete's due what?
Saturday or Friday. It's due this week.
Yes.
Both of them are due this week.
No, steel due next week.
No, next week Tuesday, I think.
Steel.
Yeah.
So concrete's the only other thing that's due this week. I'm going home, I'm sorry. I'll comfort on
I mean, where's self-weight starts to be Yeah, maybe then all I'd be looking for is just say 20%.
Yeah, that's what it's a foundation.
Yeah. Is that what part 9 is? Well, I think I'll just assess people on how they
Yeah, I asked him, just like check out. And then he said not practical na siya.
And I was like, for what?
But I didn't understand what he said. So I was like, I said, oh, okay. Oh, because I'm suggested. Parang siya. Parang si...
Yesterday, you're talking about the Trampido. The Chico got caught in the leg she got caught by someone in the next building. Having a threesome during this game. No, here in Calgary, 8 years ago.
So first half, and then second.
She's 27 right now.
So basically,
So 8 years ago means
it's just where
she was 19.
Generally, the hearing would have been checked.
Having a threesome by the street.
I know. You said it's a 9 to 5. No meetings. That's not even fair. It's one-on-one. So one.
Right now, we're doing
one.
a little backwards. We're doing columns.
There. So, parang one teacher, one student.
Yeah.
And yung nakuha niyang teacher,
Maybe that's why.
it sucks for him.
There's no.
Yeah.
Because it's a student that you check.
That you check. The difference is too.
So let's skip again.
With studs. we
Okay,
don't
I woke
have
up at like 7. Like 7. I have to leave. And I was like, I don't want to skip because I already skipped last week.
So I think
Di na ako nag-question. But like, usually,
in there.
For SPF,
Nagising niya ako at 6. Pero, tumayo ako at 6:30. Just 30.
You don't have enough information. Yeah.
Cause you know why? Cause I like, after I started parking, I didn't care. Cause I would like wake up and I was like, shit, I'm gonna miss the bus if I don't like practice. So that's like my, I guess, more.
So I would just say,
But
yeah, we'll see. I'll ask you about it. No, but we might have this on the final, right? Consider that. But on the final. Sometimes.
I think for next step, do you have a view on your laptop? I think we have these for estimating. Because I saw, I saw sina Kuya Jordan, and he was like, parang gusto yung gumagawa ng plan and stuff. I think, because he was like, nakita ko siya ng kabubi mo, and then he was like changing stuff. I was like, shit. Sabi niya, sabi niya, dito si Jeff does like mag-take a break. So there's a chance that he might be not our teacher. But yeah, if I was like, if that's true, then that's good. I don't know. Si Ben Eder. But he's teaching, only teaching estimating.
Pangit lang na teachers.
Oh,
Yeah. The intent is to do it built up. And remember in the notes, I said the headers.
I just can't wait for a surgery.
Shouldn't be in the zone.
Right? If you're in this class, you're if he just like he's not trying to he is. That's the thing about it. But like I'm not ready for like the winter surgery. Or we'll be outside during like the snow and shit. So yeah, but like our fucking camp
Still is better than 1.5.
we have to like fucking I might buy the
I don't think it's available. I'm waiting for that to be. Oh, maybe there is.
I'm just waiting for it to go on sale, but I don't know. Amazon?
Yeah, but I'm pretty sure there's still one.
Yeah, that's all you have to do.
It wasn't incorporated. No, but if I look here. I didn't follow that
If I finish the rabbit jelly, I Bro, I started to like the video.
Yeah, it's so funny.
If they remove the OG, I'm not playing. They will. Oh, it's only for them. Bro, they should. Like they should keep both of them, like the OG and then the regular. Yeah, if they do grow up,
No, I've already read it.
I like when all the
Therefore, the joystick chip.
I need to start downloading. Because it's like it's very much like Counter-Strike, but like with power. That's why I hate like those types of games because they like 3 power.
Nah, it's so fun. Like I'm not even big into shooters.
Do you remember the MR?
That's fucking I'm urgent if you could fuck with it.
Oh, I have.
And then your checklist. Yeah, checklist. You should. Okay, let's do the example. Any questions so far on exterior walls? Is the concept pretty clear? Everybody can visualize what's going on here. Visualize the failure modes are important to know. Are you guys talking about wood over there? Yeah. The failure modes are important to know because that's what we're checking for in our considerations, MR, VR. That's why I wrote it that way. VR is less than VF. MR is less than MF because those are considerations we're checking. Okay, so for the example, I'm gonna do them over here so we don't. Okay, so the question is, design an exterior wall for the McCann house on the north wall, assuming the following. Given snow loads, wind loads. How would you guys find snow and wind loads? Okay, you're doing it in concrete and snow and steel, right? So this stuff is derived from Q. Yeah. And then this is SS plus SR, right? And this will be Q, what do they call it again? QI plus Q, I don't remember it now. Okay, so I'm in NBCC here. Specified loads. loads due to snow and rain, so that's S. Alright, which is SS, SR with your accumulation factors, exposure factors, that's accumulation, base factor, all that good stuff. You guys did that in steel, right?
Concrete.
In concrete, okay, you guys did that in concrete. In this one, we didn't have a lot of time to develop this and we didn't want to repeat it, so I'm just giving you the wind loads and snow loads. Here, for the wind load, you got this P. There you go, for some reason I couldn't remember this. You got P, and then this will also be, you'll have the internal wind as well, PI. So you have a net wind from P and PI with all your tables, exposures. You guys did this in steel, okay? So P plus PI. Concrete, course, wind course. So for this, I just specified wind load and snow load. Okay, roof dead load is given, and then the construction SPF number 2 wall studs, ignore wall self-weight. So first thing you guys should do, pull up the McCann drawings. And you're going to start looking through the plans. So here's the basement floor plan. Here's the main floor plan. Start at the roof. Roof is running, trusses are running east, north, south. All right, so where's our governing exterior walls going to be? The north and south walls or the east and west walls? Why the east and west?
Because they're working the trusses.
The trusses are running north-south.
Yeah, so these are the walls that are.
Oh, yeah. Okay, terminology. I was saying the walls on the north side and the walls on the south side,
Yeah, I meant
they're gonna be running east-west. But I'm talking about, this is the ones we wanna be looking at. It's good. No, it's a good lesson, right? Like all your words are interpreted. All your words are always interpreted. So I'm talking about these walls and these walls because they're holding the roof weight. So I look at the plan and I look at if there's any sort of jogs and stuff like that. Notice this dashed line indicates a vaulted ceiling. Alright, so to get more information, we go to the sections. Here's a section through the north and south walls, running east-west. Alright, the trusses are sitting on them. You got your 2-foot overhang, so that's going to help you get your gravity loads from the roof. You're going to get the wind loads from the calculation of P and PI. And these walls here, we're going to get heights. Alright, this doesn't give really good heights. This is 14'5" to the top of the roof. These dimensions aren't helpful, but if you go to the other section, alright, now you got a different section, and you got 8'1" from the top of the floor to the top of the wall, which includes 3 plates, 2 top plates and bottom plate. Now the vaulted ceiling here, what does that do to the wall? On this side. What happens to the wall here? The wall's 8 foot here, and then the vaulted ceiling, look at the trusses got shallower, right? So that the interior space, the ceiling height gets higher. What does that do to the wall height? The wall height increases too. So now you've got 8'1". You got 8'1" plus 2'9". That's about 10'10". We're still under 11'8", so not quite tall walls. But these are going to be taller walls. And when you go and design, these will be the governing walls. Do you guys see that? Why are they governing over the other ones? What will they have a tendency to fail in more than these ones? Buckling, deflection, What will they have a tendency to fail? What would the taller walls have a tendency to fail more than the shorter ones? We said buckling, deflection,
Beer,
what?
beer.
Bearing. Bearing will be the same. A little bit more wall self-weight, but insignificant, especially since we're not considering it. Have you got them all? If you want, look back at your notes. Here's all the failure modes here. So we said buckling. When it gets taller, buckling will become a concern. What about bending? Bending too, right? The longer the height, bending becomes a concern. Shear gets higher, so all of the bending considerations that we did in Module 2, those become a concern with the taller walls. And the compression, or sorry, the crushing won't be as much. Connections will also become a concern, right? Because you have a longer span. So the right answer is the taller walls, all of these become more of a concern. And I wanted to highlight how the taller wall will,
In this case, would we have a taller wall or a wall with the same height and a gable truss on top?
taller wall.
Okay. If we
It changes, but they wouldn't do a gable truss here and then do some shorter trusses. They would continue it like this and have walls. The other thing is in the vaulted spaces, and architects like to put windows up there too. All right, and as soon as you got windows and stuff up there to let some light in, you're not going to put a truss there.
What would the view be if we're looking from the left?
For that, we have to look at the elevation. These are the north, we got to look at the elevation. So let's say that's the north and south walls, front and back. So here, it looks like a truss, right? But here you might construct a raked wall, all right, where each stud is getting successively longer, subsequently longer, and then shorter.
If there was a truss with a vaulted ceiling, so you don't have a roof raised the wall, would we have the same effective length for this wall? Because
If
we
you
have
had
the
a truss
on top.
here, that truss, if you connected a wall at the bottom chord of a truss, what do you think is going to happen there?
Because I'm not sure if the truss will be helping to resist lateral.
That's the question. Can the truss do it? Like if you, let's use our
I
highlighter
think
here.
so, but I'm not sure. Because then we would have K equals 2.
How come I can't just draw on this? This is so frustrating.
Not on your computer. Well, not on your computer.
Okay, so if the wind is coming here, I don't have to highlight the whole thing. You're basically gonna have a beam, all right, and the trib width of that beam, some of it's gonna go into the floor, and the roof is all gonna go into here. So your trib width. Let's say half the wall. That's the trib width that's going to go into the top of the wall. And if you have, and then the top of the wall is going to be trying to push into the screen, right? And the truss is going to have to support that, right? So when we look at the vaulted section here, this wall is trying to push in towards the window. What's gonna restrain it? There's nothing, right? So when you have these trusses, you can either put a huge beam across the ceiling that defeats the purpose of the vault, but if you can get it into this roof, then you've now can distribute it into the roof level here. So the other way is on this section, this becomes similar to a beam, this becomes a bending member, and it has a reaction here, and the whole thing is bending into the page. All right, so that's why what we'll do instead is we'll build a rack wall all the way up to the top, and then those we'll design those for bending. Does that answer your question?
Yeah.
That's a good question. You guys, so we'll just draw a few. All right, so we'll have a rack wall. Rake wall. Rake? Does that have a C? I don't know.
Right, R-A-K-E.
Right? Rake wall just means the studs are getting longer, they're not all uniform. Alright, so let's draw our free body diagram. So we've kind of read and understood the problem. We've got our snow load ULS, 2.7 kPa, 1.5, 1.2, all are given loads. Exterior wall studs, I got the north wall, and blah, 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 blah. So on the So here's the start of the rake of the vaulted ceiling. So then here's our tall wall. That's not our tall wall. Here's our.
Yeah.
I guess you can't draw straight lines with a highlighter. Okay, for this one, we're just going to do, to show you the process, we're going to do a standard 8-foot high wall. Okay. Design this wall. This is a typical example, all right, and this is atypical or unique.
Wouldn't those walls there, like by the vaulted ceiling, wouldn't they become rake walls as well, like higher?
Just this one will be raked. Because this one here is all, there's no vault.
Right, but the walls on the side, like where the vaulted ceiling changes, wouldn't that be raked as well?
Here?
Yeah, like this one.
No, because you would have, let's go to the elevation. At the ends here, you've got a standard height. See that?
Yeah.
So this is 8'1" on the sides, and then it gets up to 10'10" There's actually trusses here too. This isn't showing everything, but it gets up to 10'10". you'd have trusses like that. So I'm okay, you'd have your trusses up there, and then there's your wall. So as you come back down here, you're into a regular 8'10". So for this example, we're just going to talk about the conventional, the typical wall, and then this would be a unique case. That's really hard for me to do for some reason. All right. So now we've read and understood the problem. Your free body diagram look very similar all the time. I never leave myself enough space apparently. So with an exterior wall, you're always going to have a load, gravity load, acting on the studs. And you're going to have W prime F. L and that's pretty much it. That's going to be your free body diagram. All right, so from 1 over A5, L is equal to 8'1" minus 3 times 1.5 inches. 8 feet plus 1 minus 3 times 1.5 over 12, all my inches. That's going to get to 2.35 meters. Now, when we look at the gravity loads, we're going to have a free body diagram that looks like this. We've got our wall, we've got our other wall, we've got our overhang, here's WF, alright, and then we're going to have our reactions. R1, R2, which is equal to PF. Okay, do you guys see that? That's the roof truss. Alright, we're going to have our span here, L. Maybe we call this H or L prime, just so it's a little different. And then you got your overhang, we'll call that A. And that's really annoying. We've got the same overhang on both sides. So we know this is 2 feet. What is L here? So to get that, we go to our plans and we're going to see 29 feet. 29 feet, outside to outside. And what that looks like in a section, right here, this is 29 feet inside to inside, and then you'll see the dimension lines going to the outside face of the sheathing. We scroll up, this 2 foot mark is from the outside of the sheathing to the edge of the overhang. Alright, so with wood framing, we're not always going center on the plans. We're usually going to an outside face or an inside face, and it's important to understand where your dimensions are being taken. So we're just going to consider look like this. So we got 29 feet there, and we're just going to call the overhang that. Okay, in the wood design manual, I think I gotta add this to your excerpts. Alright, under chapter 11, here's chapter 11 here, it's at the back. We'll have our, oops. Here, beam, overhang one support. Take that guy. Put that in here. And we've got our, this is what we're trying to find, given here. And this is our equation to find R2. Now what we're trying to do, okay, you remember the exterior wall, right? We're basically trying, we've got studs, this is going to be in terms of kilonewton. This is going to equal WF times S, which is our spacing, right? So what is WF going to be? This is basically our we need to find WF, and that's going to be our triplet times so we're going to take W out of the equation, and to find our triplet, we're just going to look at that. Alright, so there's WF, there's W, and then what's remaining, that has to go to, that has to go in order into each stud. Okay, so triplet is equal to (29 feet plus 2 feet squared over 2 times 29 feet equals 16.57 feet, 5.05 meters. All right, so what that's saying is all of this goes into R2, roughly. And then once we're into R2, we need to multiply that by the spacing to get PF. So the PF and spacing is a variable times triplet. Okay? Times now, we gotta deal with the loads. We're still in gravity loads. So to find WF, we're gonna have load case 3. 5.05 meters times 1.25, dead load is 1 kPa, plus 1.5, 3 kPa, plus 1.0 live load 1.0 kPa on the roof. This one here, 0. We don't have to consider that one because it's a roof. All right, and this is a snow load. And this is a dead load. And that's going to equal 28.92 kilonewton per meter. Load case 4, 5.05 meters. We still have 1.25 dead. This time we have 1.4 wind. We're going to assume the wind load is 0 on the roof. You know there's uplift and stuff like that. For now we're just going to call it 0. And then we're going to have 0.5 snow. And that is going to be 13.83. Okay, so all of this per meter width of wall. So if you go back to our thing, all right, we found our WF that's going in, R2 per meter width of wall. And let's look at the wind loads now. For load case 3, we're going to have S is our variable, and which is our stud spacing. 1.25 dead load is 0. Why is it 0? Okay, we're doing lateral loads now. Why is dead load 0? Somebody know?
So, because it's slow.
What's that? Yeah, dead load's in the up-down direction. We have no dead load going in the left-right direction. We're now looking at left-right direction, the lateral loads. So in this case, for wind loads, dead load is 0. I'll just add these in here so we see. This is wind load, and this is snow load. Dead load is 0. Snow, what's snow in the left-right direction? 0. 0.4 wind, which is going to be 1 point. Okay, that was given. And you're going to get variable S times 0.6 kPa. For load case 4, we've got our variable again. Is there any dead load? This is going to be maximum wind, so we're going to have 1.5 kPa plus 1.0 times snow. Snow is 0, and that's going to be, I'm going to use a different color here, make it stand out a bit better. S times 0, 2.1. Dead load, 1.5 is the snow load, and then this is wind load. This is dead load, wind load, snow load, companion load. Okay, let's just go and check our table here. Anyway, you guys can check the table. Let's keep this purple for now. Okay, so now we're gonna look at the checklist. So in the excerpts, there's a new checklist in there called stud walls combined loading. Make sure you see that combined loading in brackets as opposed to stud walls. Okay? No combined loading. This is module 3, interior walls. Stud walls combined loading is this one. So now we're going to check our checklist. And you'll see it's a little different than what we're used to. Is the load duration short term for the combined loading condition? So the combined loading condition means both loads are acting at the same time. Alright? So we know gravity loads are not short term. We know that. Snow's going to be there for a while. Dead load's definitely going to be there for a while. Right? But the combination of that gravity load with the wind at the same time, is that going to be short? Yeah, it's a very minimal time. So then we can say 1.5 is good. Load duration standard term for the bearing of the sill plate. We got standard term here. Surface condition dry, we can assume it is because it's material free of incisions, KT is 1. Are the studs effectively pinned laterally restrained at both ends and prevented from buckling above the weak axis? Right, because it's in a stud wall system, we can say it is. Effectively pinned and laterally, that comes down to, do we have sufficient nailing to remember our failure modes? We have sufficient nails, or did we add clips if the nails were insufficient? Is the stud eccentrically less loaded, eccentrically less than equal to 1/6 of the stud depth? Okay, we talked about eccentric loading versus concentric. We're going to assume it's concentric loading, but you'll see it's very simple to take a more conservative approach as eccentric. All right, so we passed the checklist. Let's go on to designing this thing. Oh, I plugged it in here, but then I actually need to plug it in to the laptop for it to do anything. So now what we do is a trial and error approach. Start with 24 inches on center, then 16, then 12. For this course we're doing 24, 16, 12. You guys know in industry we don't go greater than 16 typically. But the wood design manual does, and so we're including it, and you guys can choose that as an option on your test. So let's start with 24 inches. So when S equals 24 inches, 0.61 meters, load case 3. PF is equal to 0.61 times 28.92 kilonewtons per meter width of wall. All right, so then you're left with, okay, and this is going to equal to, just a second, 17.63 kilonewtons. Yes, Andre?
About KD, there is a table that I found on the wood design manual that helps me to understand which factor I need to use. It's on page 929. It basically gives you KD based on the load combination that you have. I don't know if it might help.
Well, let's look at it. Let's look at it after. I want to get through this
Sure,
example.
yeah.
But yeah, it probably will help. If it helped you, it'll probably help other people. All right, so now I'm going to show you the table. We're going to go back to excerpts, and after the stud walls is the table. So it's a little different looking. All right, right away you have L. What did we say L was? 2.35. So we're going to use a conservative amount. I'm not making you do linear interpolation, so you just take the more conservative one beyond. So L, the next one is 3.0. So up to 3, this will all be the same. All right, so for that raked wall, which is almost, 10 feet, that's going to be over 3 meters, and then we're starting to come into this region here. Next thing we're going to do is we're going to look at the P prime R. Okay, I'll share the table later. I want you guys to pay attention to this example, okay? So P prime R, when you're looking at the combinations of wind and axial, you'll see that it can take 9.67 kilonewtons with almost very little wind, 0.183. But as the wind increases, your axial capacity decreases. You see that? So basically we're going to do this in 2 stages. We're going to say, what load can it support? This is up to 9.67 for a 2x4 wall. All right, and then 2x6 walls, 33.4. What load can it support? And then with that load, is the wind load less? All right, sometimes you got to go back and forth because you might find the wind load first, 0.758, and they can only support a maximum of 4.84. But we'll go through this. Then later on, we're going to check at the bottom, and you've got bearing for the stud, for crushing the plate. You got shear, 8.33, and then you got deflection, 21.2. All right, and you can imagine from your Module 2 calcs, all right, we're going to be able to figure out deflection, we're going to be able to figure out shear from our free body diagram, and we're going to know compression. And I'm just going to start this off and we'll continue this tomorrow, but to put it all together, this is greater than 9.67, therefore decrease spacing. All right, we're doing this for 2x4 walls. So right off the bat, if you're at 24 inches in the center, 17.63 is greater than the biggest number. Happens at the end of class. I guess that means it's time to stop. There ain't no snipping this time. 9.67 is the biggest number. We got to decrease spacing. So let's go to the next one. We got to decrease a lot, right? We're almost double this. So we're going to go all the way down. You can use your judgment, or you can do an intermediate step. We're going to use our judgment here, 0.302 meters. All right. So load case 3 is going to be PF 0.302 meters times 28.92, and that's going to be 8.82 kilonewtons, which is less than 9.67, therefore okay. Now let's check the wind. W prime F is equal to 0.302 meters times 0.6. Notice it's the lower case. Wind is governing in load case 3. The gravity loads are governing for load case 3. All right, so this is going to be 0.183. Now you go back to your table. And 0.183, perfect. We're equal or less to that, so we're okay. Now we got to check load case 4. Load case 4, you got to do PF again. This is gonna be the lower PF, so this is 0.302 times 13.83. And then your W prime F is going to be 0.302 times 2.1. Now the wind governs in this case. You're gonna have 4.22 kilonewtons for PF. W prime F is 0.64. So 4.22 and 0.64, you go to your table. 4.22 goes up to here, 4.84, right? And that can hold 0.758. So that'll be, this is less than 0.758, therefore okay. And this is less than 4.84, therefore okay. Now that you've satisfied both load combination 3 and 4, we're good for our check. And then tomorrow we're going to check bearing, deflection, shear.